Hi everybody. So for this checkout, I'm going to do something a little bit different. I'm going to give you a little bit of information and then you're going to do a practice problem. So the checkout is kind of like a mini lesson. But wanted to add it here because it really provides the answer to last week's checkout. You know, that the blocking of that COVID receptor, so the spike protein can't bind to the surface of the cell, is 100% related to the molecular geometry of all the individual molecules in the receptor. So the drug that is developed needs to, in many ways, be a mirror image of the molecular geometry of the receptor, right? So the shape of the molecule actually determines all of its pharmaceutical application. So that is to say that when we look at molecular geometry, we can look at one Lewis structure, but actually large molecules have many Lewis structures that comprise the whole. So anytime you have a central atom anywhere, and what I mean by that is an atom in the middle with at least two atoms on each side, you have the ability for molecular geometry. So we're going to do some practice here. Okay, and what I have up here are, I'm going to go through three large molecules. I'm going to annotate here and get my little friendly pen. Okay, so when I look at this big molecule, first off, the one thing you need to know is that when we look at big organic molecules, anytime we have a corner like that, that's a carbon. They're just not showing the carbons. Okay, so there's really carbons there. All right, so let's go through first and find out all of the central atoms. So I'm going to mark those in green. So we have a central atom here. This oxygen is a central atom because there's a hydrogen on this side and a hydrogen and a carbon on this side. Okay. This carbon, this carbon, this carbon, this carbon, this carbon, and this carbon, those are all central atoms, and they're all central, again, because there's at least two atoms on each side. These hydrogens are not central. We call these terminal, actually. There's not another atom on that side. So let's go through and let's give the molecular geometry for all of them. So first off, for this oxygen here, okay, this here, this is going to be bent. And we know that because anytime we have a central atom with at least one or two lone pairs, it's bent with a 104.5 degree bond angle. So there's that central atom, that's this, and here's one thing on the other side, and there's another thing on the other side. So that's bent. Okay, let's look at this carbon right here. This carbon is trigonal, T, planar. Now how do I know that? We know that trigonal planar means one atom up here, one atom up here, and another down here. Now, boron is the only one that could do it this way. If it's any other element, it needs to do it that way. And we know that that's a 120 degree bond angle. So if you look here at this, that central atom here is this one here, one up, one here, and one here with no lone pairs. And that's going to be the case for all the rest, and I don't need to draw them. This one here and this one there as well. They all have one central atom and at least three there. Okay, let's go to this larger molecule here. So let's find all the central atoms first. I'm just going to put dots by them. Now in this one, they are showing all of the elements. Okay, so let's start over here. This carbon, this carbon, this carbon, this carbon, this carbon, this carbon, these are all the same. Okay, these are all trigonal planar. And again, all of them are following that non-boron trigonal planar where you have a double bond here with 120 degree bond angle. Okay, now we can move over here to this one. This is also trigonal planar, even though they're showing this like that. Okay, that is the incorrect way of drawing it, right? These bonds are actually down here like that. It's still trigonal planar. And we actually see the same thing here with this oxygen. Okay, we see that this oxygen has an atom here, and lone pairs. So we know that it's bent. So in reality, this should be down to 104 degree bond angle. Okay, this one actually here is bent, and that's drawn correctly. This one here is trigonoplanar as well. Okay. Now this one here, this is a new one we haven't seen before. This is tetrahedral. And we know that tetrahedral is when you have one thing in the middle and four things around it. But we know that it's not a square like that. It forms kind of a tripod-like situation. So what we're seeing is often what we see in scale here is not what we see in reality. Let's go through and look at this. There's some shortcuts used here, and that's okay. This right here actually means that this carbon here has just 3 hydrogens around it. Not a big deal. So that's what we're seeing right there. What they're also not showing is lone pairs. Notice this nitrogen is not boron. There should be some lone pairs there. And this oxygen should have some lone pairs there. And there's actually a bond to that hydrogen. So now that we know that, let's go identify our central atoms. Well, we know that that's central. We know that's central. We know that's central. All these carbons are central. Okay. And that oxygen's central. So what is the molecular geometry here? Well, this one here has 4 things around it. So that's going to be tetrahedral. I'm just going to use a T. I'm going to say tet. We know that there's no lone pairs in 3 things here. But we know that this is not drawn to scale. The bond should actually look like that. So this is going to be T planar. And so are all of these carbons here. Those are all T planar. And this oxygen right here, this is bent. See, we got one bond here and another bond there. So in reality, it should go like that. So when you're looking at large molecules, go through and identify all of the central atoms. Make sure all the lone pairs are filled in, and then just follow your rules. Okay? It's either linear, bent, trigonoplanar, trigonopyramidal, or tetrahedral, and you are not going to see usually any linear in a large molecule like this. Okay? Take care.